Now that you've had your introduction to net redox reactions, let's do some practice. First, a little more background information that will help you in writing net redox reactions. Sometimes you will see HCl or some other strong acid as a potential species in your redox reactions. I remind you that HCl splits into H1+ and Cl1-. If you go to the standard reduction table, H+ would be involved in the standard hydrogen electrode. Chloride is a weak reducing agent. In addition, H1+ is sometimes a participant in other redox reactions. Here the H1+ does not change oxidation state. It's the oxygen that does, but the H1+ needs to be present to soak up the oxygen and make water. Many redox reactions occur in acidic solutions. Here's another example to go through. Write the spontaneous net equation for the reaction, if there is one, when a copper-coated zinc penny is placed in an aqueous solution of HCl. In chemistry speak, we're talking about solid copper, solid zinc, and HCl that's been dissolved in water. HCl is a strong acid, so we have 4 potential species that might interact in a redox reaction. Our job here is to identify the gas being given off. As a reminder of the steps, first we look up our reactions in a reduction potential table, listing them with the most negative on top and most positive on the bottom. Zinc is involved in a redox reaction with a reduction potential of minus 0.76 volts. Copper you've seen many times. Chloride is involved in a redox reaction of plus 1.36 volts. And H1+ is our standard hydrogen electrode at 0 volts. So now I have them listed, more negative on top and more positive on the bottom. Can you remember the second step? It's to imagine the orbitals on the left are empty because these are our oxidizing agents, and the orbitals on the right are full as our reducing agents. The ever-important step 3. Circle the species actually present. We have copper solid, not copper 2+. We have zinc solid, not zinc 2+. We have H1+, and we have chloride ion. Next, we need to select the pair in which the electrons travel from high energy orbitals to low energy vacant orbitals. The electrons aren't going to jump away from the nucleus, from copper to H1+, or chloride to H1+, but we do see a potential spontaneous redox reaction between zinc and H1+. So if there is a spontaneous redox reaction, remember that the top redox half reaction needs to be reversed because it is an oxidation. So I've written the standard hydrogen electrode as a reduction and turned around the zinc redox reaction so that it is an oxidation. Now we just add them so the electrons cancel. Here is our net redox reaction, and this will give off hydrogen gas. How about a look-see? In this experiment, we have 2 test tubes of 3 molar HCl. Let's investigate the reactivity of each of these with zinc metal and copper metal. In this test tube, we see bubbles starting to form around the zinc metal. In the copper test tube, no bubbles are forming around the copper metal. There appears to be no reaction. I trust you can see that a redox reaction definitely occurred between zinc metal and the aqueous solution of HCl. I want to point out to you some common mistakes when you identify and write net redox reactions. Part of this is related to vocabulary. Please notice that fluorine is F2, whereas fluoride is F1-. Remember that the ides are monoatomic anions. The enes are the elemental materials. Why does that make a difference? Well, notice that fluorine is a very good oxidizing agent, and fluoride is an extremely poor reducing agent. So knowing if you have fluorine or fluoride is going to make a difference in your answer. Another issue is knowing when you're dealing with a metal in oxidation state 0. So lead shot is lead in the 0 oxidation state, or metallic copper. If we wanted copper 2+, you would say copper ion. Silver wire, zinc coin. If it sounds like something you can hold in your hand and not something that is dissolved in solution, then it's typically oxidation state 0. And all these items you can hold in your hand as a solid. One last issue with writing redox reactions. Sometimes students forget that ionic compounds dissolve into ions. Iron 2 bromide is an ionic solid. If it dissolves into water, it does not make iron metal and bromine. That's not what happens. Yes, take your ionic solid and make sure you dissolve it into aqueous ions in solution. Let's do a little practice here. Silver wire is added to a solution of nickel 2 chloride. Here are the reduction potentials listed with negative on top and more positive on the bottom. Silver wire. Does that mean silver in the 0 oxidation state or silver 1+? I hope you say, it sounds like something I can hold in my hand, so it must be solid silver. How about nickel 2 chloride? That would be this compound right here. So are you talking about nickel in the 0 oxidation state or nickel 2+? I hope you say, that's an ionic compound, so I need the cation, nickel 2+. What about the other piece? Are you dealing with chlorine, chloride, or this unusual ion here, Cl2 1-? Once again, it's an ionic compound, so I hope you believe you're dealing with the anion chloride. Now look what happens when I actually circle what I have. Do you see any situation where the electrons belonging to items on the right can travel to empty orbitals on the left? No, there is no spontaneous reaction that occurs between these compounds. How about another one? Bromine is added to a solution of iron 2 chloride. So here are some reduction potentials listed. When you see bromine, is this going to be Br2 or Br1-? I hope you say Br2. And I will admit that bromine is not exactly that water soluble. But let's assume we're bubbling enough into the solution that there might be some interaction. Iron 2 chloride, that would be this compound right here. So, do you want Fe, Fe2+, or Fe3+? I hope you say, I need Fe2+. There's another thing I need to caution you about regarding iron. I have one redox reaction here with Fe2+. There is another one where Fe2+ is the reducing agent, and the oxidized form for that half reaction is Fe3+. Here is the iron reaction you're familiar with between iron 2+ and iron at -0.44 volts. Here is another redox reaction involving Fe2+ and Fe3+ at +0.77 volts. So when we circle Fe2+, remember that it can be both an oxidizing agent and a reducing agent. And finally, for iron 2 chloride, do you want Cl2, Cl- or Cl2 1-, which doesn't exist? How about Cl1-, chloride. Now it's our job to find some redox reaction where our reducing agent can give electrons to our oxidizing agent. And I trust you see that the half reactions in the middle are our spontaneous reaction pair. Here is our spontaneous reaction pair, and of course I leave the bottom reaction as is. This is our cathode. I take the top reaction and I turn it around. So Fe2 plus is on the reactant side, and Fe3 plus and 1 electron are on the product side. This time we need to do a little bit of balancing. You notice how we have 2 electrons going in and only 1 electron coming out. This means we need to multiply every coefficient in the top reaction by 2. So I need 2 iron 2 pluses, 2 iron 3 pluses, and 2 electrons. Now my electrons will cancel out and I can add these 2 redox reactions together. Notice how charge in equal charge out. Our net charge on the reactant side is +4, and our net charge on the product side is also +4, a balanced redox reaction. So here is your sample question. Write the net reaction when a copper strip is placed in silver acetate solution. Silver acetate is, of course, this compound right here, and you won't find acetate anywhere on our redox chart. So we're just really concerned about the silver and the copper strip. Please follow the steps and then decide which is our net spontaneous redox reaction, if any. To help you decide if there is a reaction, please watch this.
On the left we have a solution of silver nitrate containing silver 1+ ions in the dish and a piece of copper metal. On the right there is a solution of copper 2 sulfate containing copper 2+ ions and a piece of silver metal. So let's drop the metals into the ion solution. We'll take the piece of copper and put it into the solution of silver nitrate. We'll take the piece of silver and put it into the solution of copper sulfate. And we'll watch and see what happens.
Isn't that beautiful? It's just like Christmas tree tinsel.
So let's look at what has happened to our 2 pieces of metal. Clearly on the left, the copper wire now has silver attached to it on the outside. You may even be able to see a little bit of pale blue color due to copper ions, which are now in solution. Over on the right, let's pull the silver wire out of the copper solution and see what's happened. We'll set it on a paper towel. Doesn't look any different. In fact, if I take another piece of silver and put it next to it, no reaction has happened. So again, we get a reaction on one side with the copper metal in the silver ion, but not on the right-hand side with the silver metal in the copper ion.
So clearly a redox reaction occurs. Let's try another one. Write the net reaction, or none, for the following. Aluminium foil is added to a solution of copper 2 chloride. I've written your half reactions from the reduction potential table. I want to highlight something for you concerning the water reduction reaction. You may notice on the table that there are two reactions exactly the same, but with different reduction potentials. There is this reaction with water as the oxidizing reagent at minus 0.83, and this reaction with water as the oxidizing agent at minus 0.41, and a star next to it. The star indicates that that half-cell potential is for water at pH 7, not at standard state where hydroxide is 1 molar, which is pH 13, a much more basic pH. So as you get into more advanced chemistry courses, you'll realize that the reduction potential changes as the pH changes. For this particular reaction, we're going to use water at neutral pH 7. To help you decide if a reaction occurs, let's watch this video. In this experiment, we're going to investigate the reaction of aluminum with copper chloride. We'll see if there is a reaction. On the left, we have a beaker of water for comparison, and I will put some aluminum foil in this beaker of water. In the middle, we have a solution of copper chloride, and I will put aluminum foil in this solution. We have the same concentration on the right of copper chloride just for comparison. As you can see, the aluminum in the copper chloride is starting to form bubbles. You may also notice some darkening of the aluminum foil. All right, it's time to rescue our aluminum from the copper chloride. Let's pull this out, and you notice that the test tube with the aluminum has become lighter where the aluminum has been reacting. The test tube on the right, which is our standard, is unchanged. Now let's compare the aluminum left in the water to the aluminum left in the copper chloride. The aluminum that we pulled out of the water appears to be unchanged. The aluminum that we pulled out of the copper chloride solution appears to have a reddish coating on the outside. I imagine you can guess what metal that is. So a couple things about this particular set of reactions. There's actually two redox reactions going on. I've written the redox reaction that has the larger fall or difference in voltage, but since you saw bubbles occurring, you must realize that the reaction with the lower voltage is also occurring. Why wasn't that occurring just with aluminium in water? Well, it does, but I think the presence of the copper 2+ caused an exothermic reaction, so the water temperature rose, and we saw much more vigorous reaction with the aluminium copper 2+ solution than we would with aluminium and water. Another question for you. A lead bar is placed in bromine and water. Our assumption is that enough of the bromine dissolves in water that we can consider the reaction that might occur. I also want to point out to you this redox reaction involving water as the reducing agent. Just like the previous example, this reaction is on the chart twice, depending on the pH. Here it is with the star next to it for neutral water at pH 7. And here it is again at standard state when the H1+ concentration is 1 molar. I'm sorry that I don't have a video for this reaction, but I think you can figure it out. Once again, we're identifying the redox reaction with the greater voltage difference. Here is another one for you. Metallic copper is placed in a solution of potassium iodide. How about if we bubble chlorine gas into a solution containing iron 2+ ions? And finally, this would be the challenge question. What if iron 2 sulfate is added to an acidic solution of potassium dichromate? Yes, this seems quite horrible. However, I think you can do it if you follow the 5 steps. And it's a real reaction. This particular titration is used to determine the iron content in steel. First, they digest the iron with acid into ions, and then they perform the titration. So I have faith in you. You can do it. And just for fun, let's watch the reaction.
For this experiment, let's investigate the reaction of an acidic solution of potassium dichromate with a solution of iron sulfate. The potassium dichromate in solution is orange. The iron sulfate solution is colorless. Let's mix them together. As you can see, a greenish-yellow color has appeared.
Yes, students always like that video because that is proof that even I can sometimes be clumsy in lab. So if you're ever clumsy in lab, remember, we all do it.